Hello and welcome to the next lecture. Today we're talking about Laplace transforms of periodic functions, and we'll also talk about the concept of a system transfer function. The reason we single out periodic functions as a separate topic is because their Laplace transforms have a very specific form. So let's define the periodic functions first. A periodic function are precisely the functions for which there exists a positive number t so that a function f shifted by capital T gives us exactly the same values as f at t. We know quite a few periodic functions. Trigonometric functions like sines and cosines are periodic with a period 2 pi. Tangent is periodic with a period pi. There are also special periodic functions, like for example a square wave. The smallest possible number t that makes the expression above to hold is called a fundamental period. Sometimes it's also called a basic period or a prime period. It's easy to see that the functions that are periodic with the period t are also periodic with the period 2t or 3t, and the fundamental period is the smallest possible period for the function f. When we compute Laplace transforms of these functions, we can exploit the fact that the function f repeats itself many times. So I'm going to split the integration into an integration over the first period plus the integration over the second period etc, etc, etc. In general, I can write it as a summation as an integration that comes from the period endpoint kt to the endpoint of that period. At this point, I'm going to employ change variables. I'm going to say that tau is going to be t minus kt. In other words, t is tau plus kt. Then dt is the same as d tau. And every integral now has limits from 0 to t. So this is going to be the summation of integrals that integrate from 0 to capital T f of tau plus kt times e to the minus s multiplied by tau plus kt d tau. Since the functions are periodic, each one of those integrals can be viewed as integration of just f of tau and I can break apart the exponential into a product. Which I can simplify into a summation. And I write exponential e to the minus skt as e to the minus st to the power k. And then we can write the Laplace transform of the whole function f as a summation of the Laplace transform of just one period of the function times e to the minus st to the power k. Since the Laplace transform of one period is something that's independent of k, we can move it outside. And what's left is a summation of e to the minus st to the power k. K goes from 0 to infinity. Since e to the minus st is a constant for every s, we can view it as a geometric series. And a geometric series has a very easy formula for summation. It's 1 over 1 minus e to the minus st. Therefore, the Laplace transform of the periodic function f of t is 1 over 1 minus e to the minus st times the Laplace transform of just one period of the function f of t. This result is quite natural, since the function is repeated many times. We can view it as a summation of one period of f shifted many times and then added together. And since the shifts in Laplace transform mean a multiplication by an exponential factor, that's exactly what happens outside of the integral. And then we add all of those exponential factors together, we get this fraction, because the summation of exponential factors is just the sum of the geometric series. I want to add a little remark here. The formula we derived isn't going to be used in the form that I derived it. Most of the time, we're going to use the summation formula instead, because the summation formula will let us invert the Laplace transform into something that will be then re-expressed as a summation of shifts. When we write the Laplace transform of f of t as a summation of e to the minus st with a capital T raised to the power k times the Laplace transform of a single period of f. And therefore we prove the theorem that the function f of t be a periodic function then the Laplace transform of f can be written as a function a Laplace transform of a single period of f. Or as a summation of shifted periods of f of t. Let's look at a couple of simple examples. In this case, the function f of t is a sort of a square wave that is starting at 1, then is shifting to 0, then is shifting to 1, then is shifting back to 0. And that keeps going indefinitely. Before we write down the Laplace transform, I want to ask you a question. What is the period of this function? If you said the period equals 2, you're exactly right. Remember, the definition of a period is the time interval after which the function starts to repeat itself. If you said something like 4 or 6 or any other even number, you're also right. But I think it will be more proper to say that the period is equal to 2. Let's compute first the Laplace transform of a single period, which means we have to integrate from 0 to 2 the function f of t times e to the minus st dt. Well, that means that we only have to integrate from 0 to 1, because that's the only time interval where the function f of t is non-zero. And on that time interval it's equal to 1. And that means we have to evaluate the entire derivative from 0 to 1. And that means it's e to the minus s minus 1 over minus s. So it's 1 minus e to the minus s over s. Obviously, I could have written it slightly differently. I could have said that f of t is just a linear combination of two Heaviside functions. And you've done this before in your homework. Here I just wanted to use the definition of the Laplace transform, since this is going to be the easiest way to find this particular Laplace transform. In other cases, it might be more beneficial to express the function as a linear combination of functions multiplied by Heaviside functions. Anyway, the final answer (1 over 1 minus e to the minus 2s multiplied by 1 minus e to the minus s over s. This can be simplified if you wanted to. I can write 1 minus e to the minus 2s as 1 minus e to the minus s times 1 plus e to the minus s. And there is also a factor of s. And therefore this can be written as 1 plus e to the minus s over s for s strictly greater than 0. Obviously, when s is equal to 0, this expression doesn't make much sense. The simplification that I just did is not totally necessary, but it might help in some situations. Let's look at another function. This function is a little bit different. It's a so-called sawtooth wave. The function emerges at 0 and goes as a function t all the way up to 2, where it repeats itself. and then jumps back down, and then repeats itself again. You can see why it's called sawtooth wave. The waves like this, and the square wave above, arise very often in the theory of analysis of digital circuits. So it's not a purely analytical exercise here. So let's see what's the Laplace transform of this function. First, we need to compute the integral from 0 to capital T. And we can clearly see that the function repeats itself after 2 units. And the function is just always equals to T. So all we need to do is to evaluate this integral. The entire derivative is minus t over s e to the minus st minus 1 over s squared e to the minus st. This entire derivative needs to be evaluated from 0 to 2. And this gives us minus 2 over s e to the minus 2s minus 1 over s squared e to the minus 2s. And when t is 0, minus 1 over s squared. That's what's left of the expression when t is 0. Simplifying this, we get minus 2s minus 1 times e to the minus 2s plus 1 over s squared. We can simplify it slightly by writing it as 1 minus e to the minus 2s as 1 plus 2s over s squared. Just to show you that doing this with the Heaviside functions is going to give us the same exact result, we can write a single period of g of t as h of t minus h of t minus 2 multiplied by t. I guess it would be easier to take a look at this as a moment. H of t has a Laplace transform 1 over s, and h of t minus 2 has a Laplace transform e to the minus 2s over s. And multiplying by t means we need to take the derivative of it. Take a derivative 1 over s, and we get minus 1 over s squared. And the minus minus cancels out, giving us 1 over s squared. And then we also have a derivative of e to the minus 2s over s, which gives us minus e to the minus 2s over s squared minus 2 e to the minus 2s over s. And this simplifies into exactly the same function that I just written above. So regardless how you do it, you're always going to get the same Laplace transform. Therefore, the Laplace transform of the whole function g of t is going to be 1 over 1 minus e to the minus 2s multiplied by 1 minus e to the minus 2s multiplied by 1 plus 2s divided by s squared. Let's look at a couple of examples where a periodic force is applied to a physical system. In this particular case, we need to derive an expression for the velocity of a projectile that's being driven by a periodic on-off force, and the projectile is moving in a viscous media that exerts a drag force proportional to the velocity. If we use the Newton's law to write the differential equation, we get that mass times acceleration should be the sum of the forces. And one of the force is the drag force proportional to the velocity. but there's also this periodic thrust. Since m is 1 and gamma is 1, this translates into the following initial value problem. I'm going to say that v of 0 equals v naught since it's not given. And later on we're going to play around with Mathematica with this number to see what effect this will have. You can also see that because f of t is piecewise constant, we can see that when f of t is 1, a stable state will be when v is exactly 1. And when f of t is 0, the stable state is going to be when v is exactly 0. By steady state, I mean the state in which v prime is 0. Therefore, we're going to see that switching f will have an effect of velocity starting to tend to 1 or starting to tend to 0. Let's see if my intuition is correct. Let's use the Laplace transform on this equation. Laplace transform of differential equation is going to be s times v of s minus v naught plus v of s equals the Laplace transform of f of t. But we already found the Laplace transform of f of t in one of the previous examples. So it's simply 1 over 1 minus e to the minus 2s times 1 minus e to the minus s over s. Well, I'm going to use the summation definition because this way it's going to be easier to invert the Laplace transform. So it's 1 minus e to the minus s over s multiplied by summation of e to the minus 2s to the power k, where k goes from 0 to infinity. Simplifying, this leads to v of s multiplied by 1 plus s equals v naught plus 1 minus e to the minus s over s times the summation of e to the minus 2ks when k goes from 0 to infinity. Therefore, the final version of v of s is v naught over 1 plus s plus 1 minus e to the minus s over 1 plus s times s times the summation k goes from 0 to infinity of e to the minus 2ks. Multiplying by an exponential factor means that the original function should be shifted. So this will only produce the shift in the inverse Laplace transform. So what we're interested in is the inverse Laplace transform of v naught over 1 plus s, and that simply is v naught times e to the minus t, and the inverse Laplace transform of 1 minus e to the minus s over 1 plus s over s. This can be written as the inverse Laplace transform of 1 over 1 plus s times s minus the inverse Laplace transform of 1 plus s times s shifted by shifted by 1. The inverse Laplace transform of 1 over 1 plus s times s is the inverse Laplace transform of 1 over s minus 1 over 1 plus s. So this is simply a Heaviside function minus e to the minus t times h of t for the first inverse Laplace transform, and the second Laplace transform is h of t minus 1 minus e to the minus t minus 1 times h of t minus 1. So this is a Laplace transform of a single period, and therefore v of t will be the sum of the Laplace transform of the first term, which is v naught times e to the minus t, plus the sum, okay, it goes from 0 to infinity, of this big term. We get h, and we have to shift it by 2k. So t minus 2k minus e to the minus t minus 2k times h of a t minus 2k minus h of t minus 2k minus 1 minus e to the minus t minus 2k minus 1 times h of t minus 2k minus 1. Plotting this by hand will be slightly too complicated, so let's switch to Mathematica. So I want to repeat the process with Mathematica, and the first thing we did is we computed the Laplace transform of function f of t of a single period of f of t. And Laplace transform does everything on the infinite time interval, so I'm going to say that f of t is just a Heaviside function of t minus the Heaviside function of t minus 1. So this function is going to be non-zero only for t between 0 and 1. And hence it doesn't really matter if we integrate from 0 to 1, from 0 to 2, or from 0 to infinity, the result is going to be always the same. And this is exactly the Laplace transform that I've got for the function f of t when I integrate from 0 to 2. The next thing we did is we converted this into the Laplace transform of the whole function f of t by multiplying it by 1 over 1 minus e to the minus 2s. However, I don't recommend doing that because this will compute the Laplace transform of the whole infinite function, and sometimes we don't really need to do it. So instead I'm going to write it as a sum of e to the minus 2s raised to the power k, and let k go from 0, but not to infinity, because we don't have infinite amount of resources and infinite amount of time to wait for the Mathematica to finish the computation. I'm going to add only some small number of terms, because each one of the exponential factors here in the Laplace transform domain means a shift in the time. And if we look at the finite time domain, then at some point all of those shifts are going to be outside of the time domain that we're looking at, and therefore they won't matter for the big picture. So it is absolutely okay here to add only a few terms. Well, this was the Laplace transform of the function f. And remember that we had the equation that v of s was v naught plus the Laplace transform of f multiplied by 1 over 1 plus s. So this was the Laplace transform of v. And what we need to do is we need to compute the inverse Laplace transform of this. However, this inverse Laplace transform cannot be computed unless we tell Mathematica what v naught is and what n is. So what I'm going to do is I'm going to define a new function that will depend on the parameters v naught and also the parameter nn. and that's going to be the new function. Now I want to plot it. But because I know that Mathematica doesn't deal with sums very efficiently, what I'm going to do is I'm going to run it as a pre-computed computation. So first, I pre-compute v by evaluating this expression. So let's say the first initial velocity is 0, and let's look at the first two periods added. And let's plot the function vc in terms of t from 0 to say 10. So we can see that this function has a somewhat periodic behavior up to 6, and then things stop. It's only done because I only do the first two periods, and as a result I didn't add enough terms to cover up the whole domain. So if I add first 4 periods, then I will get a better picture. What if I want to find out what's going on outside of this domain? Well, then you can see that I really need to add a few more terms. So I'm going to add, since it's going from 0 to 30 and the period is 2, I need to add the first 15 terms. And here it is. What we see here is, if I switch back, is that the very first term right here, v naught times e to the minus t, is having an influence in the beginning of the time. And then all of those terms are going to be slowly adding to each other. What if the initial velocity was different? What if the initial velocity was 2? Well, this is what happens. The velocity very quickly decreases, and then it oscillates in a stable manner between something like 0.3 to something like 0.75. What if the initial velocity was 1? Well, this is what we're going to see. For the period from 0 to 1, velocity equals 1 was a stable state. And then the function turned off and the stable state is 0. So the velocity started to converge to 0. And then the function turned on again, and then it started to converge to 1, and then turned off again, and then turned on again, etc., etc., etc. So again, no matter what we do, no matter where we start, the velocity quickly reduces to this semi-stable pattern of behavior. In this example, we see that the framework of Laplace transforms and a little trick we learned for the Laplace transform of periodic functions helped us to get the solution in a much quicker and easier way than what we could do with just methods of differential equations. Let's look at another example. In this example, we have a spring mass system with a mass 1 and a natural frequency omega. The system starts at rest and is being excited by a square wave function that's slightly different than the square wave that we looked at before. This time the square wave oscillates between 1 and -1. Let's first compute the Laplace transform of f of t. Since it's a periodic function with the period 2, it's going to be the sum of e to the minus 2 ks, with k going from 0 to infinity, multiplied by the Laplace transform of a single period, which I can write as h of t minus 2h of t minus 1 plus h of t minus 2. This is going to be the function that is going to be 1 at 0, then jump to -1 at t equals 1, and jump back to 0 at t equals 2. Going to be the sum k going from 0 to infinity e to the minus 2 ks multiplied by 1 over s minus 2 e to the minus s over s plus e to the minus 2s over s. So we can simplify it as k going from 0 to infinity e to the minus 2 ks multiplied by 1 minus 2 e to the minus s plus e to the minus 2s over s. You can also find the Laplace transform of a single period of this function by just performing integration from 0 to 2 of the function f of t multiplied by e to the minus st. and I can guarantee you're going to get the same result. Apply the Laplace transform to the equation. We get the Laplace transform of y double prime plus omega squared times y should be the same as the Laplace transform of f of t. And this translates into the equation that s squared times y of s minus s times the initial condition minus the initial velocity plus omega squared times y of s should be the same as 1 minus 2 e to the minus s plus e to the minus 2s over s multiplied by the sum of e to the minus 2ks when k goes from 0 to infinity. Solving for y of s gives us the following. And all we need to do now is to invert this Laplace transform to get y of t. Again, this is easier to do with Mathematica. So we need the inverse Laplace transform of 1 over s times s squared plus omega squared, and at the top we had 1 minus 2 e of minus s plus e of minus 2s. This expression looks complicated, but this is already in the simplest form possible, because if I try to simplify it, it's going to be exactly the same. This time, instead of putting the sum into the inverse Laplace transform, what I'm going to do is I'm going to use this inverse Laplace transform as a fundamental period of y. It's a function of t. It also depends on the frequency omega. And the y of t is going to be the sum of shifted copies of the fundamental periods of y. So it's going to be depending on t, omega, and the number of terms that I'm going to add. So it's going to be the sum of the number of shifted of t minus 2k Heaviside function of t minus 2k. K will go from 0 to an n. And the fundamental period of y has a parameter omega in it. And I'm going to plot it in very much the same way I plotted the previous example. I'm going to pre-compute the quantity yc. Let's say that the natural frequency of my system is 2. And let's add the first 10 terms. And let's plot the solution for t going from 0 to say 100. And we can see that the solution changes its behavior at about 20. But since the period of the oscillation is 2 and I only added 10 terms, that means that I don't have enough to cover the whole interval from 0 to 100. In order to do that, I need to add 50 terms. And now we can see that when we have all 50 terms added together, we covered the whole interval from 0 to 100. And we get the right solution. The problem with the function having those breaks is because Mathematica treats Heaviside functions as a discontinuous function, and it tries to accommodate for it. I'm going to ask Mathematica not to try to optimize for discontinuities and just keep going. So the natural frequency is expressed in radians, and the frequency oscillations is about 1/2 Hz because it takes about 2 time units to complete a full oscillation. So if we want to express the frequency of 1/2 Hz in radians, we have to multiply it by 2 pi. So if we get our natural frequency close to 2 pi times 1/2, which is about pi, we start getting phenomena that is close to resonance. So what if I get exactly pi as a natural frequency of my system? Then I can say that I get something that resembles the resonance. The initial straight line right here is an artifact. If I don't add as many terms, let's say I add the first 20, and only plot the solution for 40 seconds, and I can see that this is the solution that I get. I'm pretty sure most of you have experienced this phenomenon when you're swinging on a swing as a kid, when you applied the force that abruptly changed at specified time intervals to maximize your amplitude. I want to reiterate a few points that I think are important. So when we compute the solutions using the Laplace transform, and when the Laplace transform calls for Laplace transform periodic functions, I would recommend to do the Laplace transform of only one period and then multiply it by a summation term rather than by a fraction term. The reason to do that is that every single term in the summation leads to a shift later on when we do inverse Laplace transforms. And so when you do the inverse Laplace transforms, all you end up with is a collection of shifts of the inverse Laplace transform of your solution. It's quite impossible to do that, even with Mathematica, if you just do the inverse Laplace transform with the fraction term. Let me demonstrate. So what if I take the Laplace transform of this function let me plot it. When I multiply this by a sum of exponential terms, where k goes from 0 to some predetermined number, let's call this inf L. Then plotting it is okay. As you can see, I had just enough terms to cover the interval from 0 to 10, but not enough terms to cover the interval from 0 to 20. So I can do that by adding more terms. And here we have it. Watch what happens if I change the summation into a fraction. that would be 1 minus exponential of minus 2s. Well, the Mathematica doesn't know what to do with it, because this is going to involve an infinite computation. So the Mathematica keeps it as it is. Even the all-powerful Mathematica does not know what to do with expressions that will involve the infinite summation. So hence the reason we do it the complicated way and keeping things in the summation, just because when we keep it in the summation, we can only add the finitely many terms of the summation and get away with just that, because the other summation terms will lead to the shifts that shift outside of the time interval that we're looking at right now. And although the Laplace transform with the fraction term right here looks a lot cleaner, it still takes infinite amount of resources and infinite amount of time to invert. So the last thing I want to consider today is the concept of the system transfer function. What we have seen in many of our examples when we looked at the initial value problems, most of the time the Laplace transform of the solution y is the Laplace transform of the right hand side multiplied by a very special function that depends only on the differential equation that we have. So suppose we have a system which we know can be represented as a spring mesh dashboard system. So what we have inside is a spring and a dashpot. And the whole thing has a mass m, and the spring has a constant k, and the dashpot has a constant omega. We can apply any force that we wish to it, and we can observe the reaction of the system. So the differential equation for this situation will look like m times y double prime plus gamma times y prime plus ky equals the forcing term. And the initial conditions are y naught and y naught prime. So suppose we applied some forcing to it and we observe the reaction. Can we determine the coefficients k, gamma, and m? Well, if we apply Laplace transform to the system, Laplace transform of my double prime plus gamma y prime plus ky should be equal to the Laplace transform of f of t. So since we know what f of t is, let's call it f of s. Computing the Laplace transforms, we get m times s squared times ys minus s times y naught minus y naught prime plus gamma times s y of s minus y naught plus k times y of s should be equal to capital F of s. Collecting the terms of y of s, we get that y of s times ms squared plus gamma s plus k should be equal to ms y naught minus m y naught prime plus m y naught prime plus gamma y naught plus f of s. Well, if we approach the system when it was initially at rest and then applied the forcing f of t, then y naught and y naught prime were 0 at the time. And so that's exactly what we're going to do. We're going to assume that the system was initially at rest and all of these terms are 0. And therefore, under these conditions, y of s can be written as 1 over ms squared plus gamma of s plus k times f of s. And what we can see is that this term that I'm going to highlight blue here depends only on the differential equation. In other words, it depends only on the parameters of the system. What we can see here is the Laplace transform of y of t will always be a multiple of the Laplace transform of the forcing term and this fraction that depends only on the parameters m, gamma, and k. And therefore this multiplication is always going to be happening to whatever the forcing term would apply to the system. And since we observed this kind of effect, for all of the initial value problems we considered, this term is given a special name. It's called the system transfer function. And for any linear time-independent system that we're going to consider, this is always going to be the effect. If we approach the system at rest and we apply some external forcing, then the Laplace transform of the reaction of the system is going to be the Laplace transform of the forcing times a certain function that depends only on the internal parameters of the system. Hence, y of s can always be written as the system transfer function times the Laplace transform of the input. If the capital F of s is non-zero, we can determine the system transfer function by taking the Laplace transform of the reaction of the system and divide it by the Laplace transform of the input. And once we know the system transfer function, we can predict the reaction of the system to any other input. So for any other input, let's call it g of t, the reaction of the system will be the inverse Laplace transform of the system transfer function multiplied by the Laplace transform of the input. The concept of the system transfer function is used extensively in the topics like control systems and the analysis of electrical circuit and the digital circuits. Another framework where this concept of system transfer function is useful is when we have cascaded systems. When one system has another one as its input, we can look at it in this diagram. We have a signal f of t applied to one black box system. And its output is used as an input for the second system. and the output of the second system needs to be predicted. Let's assume for the moment that both of the systems are the spring mass dashboard system, with their own masses, with their own damping coefficients, and their own spring constants. And you might say, well, where do people employ two springs connected in succession to achieve any engineering task? And there's a simple thing as your car suspension is an example of such a connected cascaded system, where you have the suspension parts like springs and dampers, but you also have the tire that also acts as a little spring with its own damping coefficient. So if you want to model the reaction of the car suspension to the road conditions, you really have to model as two springs connected to each other. In this case, we have two differential equations describing the system. And let's say that the system initially was at rest. And we have a second differential equation. And the input to the second system is y1 of t. And again, let's assume that everything is at rest for now. Then the equations in the Laplace transform domain will look like this. So the Laplace transform of the output will be Laplace transform of the input multiplied by the system transfer function. And as a result, if we consider this the first system transfer function, and this is the second system transfer function, then the Laplace transform of the output can be written as a successive multiplication of the input signal Laplace transform f of s by the system transfer functions for each one of the components of the cascaded system. You can imagine how such framework can simplify engineering calculations, but for us it's going to stay a little theoretical exercise. So let's look at a quick and simple example. I have a system that when it was excited at rest by a function f1 of t equals t, then the output measured was this expression. And the question is, what if the system, when it is at rest, was excited with a different force e to the minus t? What would be the reaction of the system? And this question can be answered very easily with the concept of a system transfer function. So the first thing we need to do is we need to find the system transfer function for this system. For that, we need to compute the Laplace transform of f1 of t, which is Laplace transform of t, which is 1 over s squared. And we also need to compute the Laplace transform of the reaction, which is going to be 1/8 is considered 1/8 of the Heaviside function, so it's going to be 1 over 8s. E to the minus 2t has a Laplace transform 1 over s plus 2, so it's going to be 1 over 8 times 1 over s plus 2. t has a Laplace transform 1 over s squared. And t squared has a Laplace transform 2 over s cubed. In order to see the system transfer function, we need to simplify this fraction. And this simplifies into 1 over s cubed times s plus 2. And therefore, we can rewrite it as 1 over s times s plus 2 times 1 over s squared, which was the Laplace transform of the input signal. Thus, the system transfer function is the ratio of the Laplace transform of the output divided by the Laplace transform of the input. So it's 1 over s times s plus 2. Having determined the system transfer function, we can now determine the output when the forcing changed. We can compute the output by applying the system transfer function to the Laplace transform of f2 of t is simply the Laplace transform of e to the minus t, which is 1 over s plus 1. Therefore, y of s will be the system transfer function times 1 over s plus 1. Therefore, it is 1 over s times s plus 2 times s plus 1, which has a very simple partial fraction decomposition. 1 over 2s minus 1 over s plus 1 plus 1 half times 1 over s plus 2. Therefore, y of t, which is the inverse Laplace transform of y of s, is simply 1 half of Heaviside function minus e to the minus t plus 1 half e to the minus 2t. And for positive t, this equals to 1 half minus e to the minus t plus 1 half e to the minus 2t. Again, let's switch to Mathematica to quickly confirm our computations. We need the Laplace transform of the input, which was t, and the Laplace transform of the output, which was 1 over 8 minus 1 over 8 of e to the minus 2t minus t over 4 plus t squared over 4. And let's simplify it. So the system transfer function is going to be equal to the Laplace transform of the output divided by the Laplace transform of input. Now let's compute the Laplace transform of the new input. So let's compute that and multiply it by the system transfer function, and then compute the inverse. Well, mathematically simplified it a little bit, but if I expand it, I get exactly the terms that I've got in my answer. Let's look at the last example that we have today. So again, we have the pair of input and output functions given, and the system was initially at rest. And then sometime after, the system was excited again with a slightly different force, but the system was initially at the position 2 with the 0 initial velocity. And the measured output has this expression. So the question is, what kind of force was applied to the system? Well, this question can again be answered with the concept of system transfer functions. We compute the system transfer function using the information given us in the first half of this problem. So we know that the Laplace transform of the first forcing term is simply 3 over s, and the Laplace transform of the reaction of the system simply 1 over s minus 1 over s plus 3, which can be simplified as 3 over s times s plus 3. Given this, the system transfer function must be simply 1 over s plus 3. Alright, we do know that the Laplace transform of the output can be computed as, well, t produces the derivative with the minus sign of the Laplace transform of the e to the minus 3t, which is 1 over s plus 3, plus 2 Laplace transforms of e to the minus 3t. And then the next term is just a shift. So it's going to be e to the minus s multiplied by the Laplace transform 1 minus e to the minus 3t multiplied by h of t. Well, computing this gives us 1 over s plus 3 squared plus 2 over s plus 3 plus e to the minus s multiplied by 1 over s minus 1 over s plus 3. We do know that since the function initially started with y0 equals 2, I know that this particular term comes from the initial condition. Therefore, the forcing term must have come from the terms inside the parentheses. And this was a system transfer function. Therefore, the Laplace transform of the forcing term must be 1 over s plus 3 plus e to the minus s times 3 over s, which means that the second forcing term must be e to the minus 3t plus 3 h of t minus 1. This problem is slightly different from the problems we considered above because the system was not at rest, and therefore some extra terms appeared in the Laplace transform of the system reaction. And therefore it is important, when we try to measure the system transfer function, to have the assumption that the system was initially at rest satisfied, so that we don't have extra terms and may pollute the output and make the finding of the system transfer function a little bit more complicated. Alright, this was almost it for today. The last thing I want to do is take a careful look at what we've done today, just to organize our thoughts and look at the big picture. We looked at the Laplace transform of the periodic functions, and we can see that the Laplace transform of a periodic function is the Laplace transform of a single period of the function f of t times this fractional term, which comes from the period of the function. I also said that it will be a lot easier for us to express the Laplace transform of a periodic function as a Laplace transform of a single period times the summation term, which will later on make it possible for us to find the inverse Laplace transforms. We looked at a couple of examples, and we also looked at the two applications of this theorem. And here I used the summation terms to invert the Laplace transforms, just because without the summation the inversion is impossible. Here I find the Laplace transform of the periodic function, and I solve for the Laplace transform of the function v of s. And then I find the Laplace transform of a single period that comes from this big formula. And then what I've done is I took this Laplace transform and I shifted several times, and then I added all the shifts. This produced an interesting effect in our mathematical computation. When we had the term e to the minus t here having an effect in the beginning, after which the periodic forcing term is the major driving force of the system. Last thing we did today is we looked at the concept of the system transfer function. The system transfer function is just a name of this multiplicative term that defines the Laplace transform of the reaction of the system. The forcing term is here on the right, and then the system transfer function is determined by this fraction that is determined by the properties of the system. In example 2, the system transfer function was 1 over 1 plus s, because that's what the forcing term was multiplied by. We looked at a few examples when not knowing the parameters of the system didn't really matter much, for as long as we know the system transfer function. And the system transfer function can be determined if we know both the input and the output, and we also know that the system was initially at rest. When the system is not at rest, extra terms appear in the calculation, and we really have to be careful in order to not forget about them and extract the parts that depend on the initial conditions and the parts that depend on the forcing and the system transfer function parts. Alright, this is where we're going to end today. I know that this lecture was quite intensive today, and there was a lot of new things that I shared with you today. We looked at the Laplace transform of the periodic functions, and we looked at the concept of system transfer function. Both of the concepts are not very complicated, and in my opinion, the best way to understand this concept is to try out a few examples yourself. So I encourage you to look at the homework and come back with your questions to me. Thank you, and I'll see you in the next video.